Hello everyone and welcome back to Causality with Boris, on broadcast from Sobolev Spaces. In this video I talk about inverse probability weighting. Its rationale, formula and the equivalence with stratifications are the three main things in this video. Make sure you review the takeaways at the end. And there is a material that goes along with this video, a link in the description. Epidemiologists invented the stratification estimator. We average stratum-specific outcome probabilities over the distribution of strata in the study population. Yet, it's not the only estimator in town. Statisticians invented inverse probability weighting. In the early 1950s, Horvitz and Thompson were dealing with samples that don't represent the target population, like in surveys. Here is their idea. Suppose we know the sampling probability. Then weighting observations by its inverse can inflate the proportion of underrepresented observations. This reasoning is linked to the potential outcomes. In this framework, we find the expected outcome if all units in the study population were assigned to the same treatment, yet using outcomes of observed treatments. By applying inverse probability, we simply change the proportion of outcomes in the treatment groups. So instead of comparing two treatment groups, we compare two hypothetical populations. They have identical distributions of stratification variables. They are equal in size, but each population has a different treatment. Then we compare the mean potential outcomes between these two populations as if they were representative of the target population assigned to alternative treatments. First, the stratification approach. It finds outcome probability by treatment within each stratum. Then it's weighting the stratum-specific probabilities by the strata proportion in the study population. That is, by the proportion of observations in individual strata relative to the entire study population. That's the sum of observations in both treatment groups. Conditional outcome probabilities come from treatment groups, and they are multiplied by the proportion of observation in strata. Now the treatment probability weighting. It finds the joint probability of treatment, outcome, and stratum for the entire study population. Then the joint probability is weighted by the inverse probability of being in a treatment group within each stratum. This method produces identical strata distribution across treatment groups after the observations are weighted by the inverse probability of being sampled with their actual treatment assignment within their respective strata. And now the promised equivalence between two estimators. Let's see it on paper. We only need four numbers to prove the equivalence. Capital N is the total number of observations in the study population. Small case n sub s is the number of observations in stratum S. Small case n with two subscripts s and a refers to the number of observations in strata S and treatment group A. Then there is a small case e sub s and a for the number of outcomes in stratum S and group A. Enter the Pearl stratification formula. It gives us marginal risk in group A by multiplying two proportions. The number of events among units with treatment A in stratum S, that's the conditional outcome probability given treatment in strata, and the number of units in stratum S relative to the total number of observations N. That's the probability of the respective strata in the study population. And that's the equation on the top. Now look at the second line here. It's the inverse probability weighting formula. It shows a product of one proportion and the inverse of another proportion. The first is the number of outcomes for strata S and treatment A among all units. That's the joint probability. Second is the number of units with treatment A in stratum S relative to the number of units in the stratum. That's the probability of being sampled with treatment A given strata S. and we use the inverse of that. We rearrange the number under the sum to get the formula that is identical to the stratification estimator. Promise made, promise kept. In our running example, we compare in-hospital mortality by the timing of surgery after hip fracture. In the absence of randomization, surgical timing has an even distribution. 23% of patients underwent surgery on the day of their admission to hospital, 44% on inpatient day 2, 21% on day 3, and 12% after that. We created 64 strata by combining age, treatment period, hospital type, procedure type, and health status. Time to surgery varied significantly within the strata. Look at this diagram. The left panel shows the observed proportions of surgeries by inpatient day within strata. And in all panels, we ordered strata by proportions of observations in the admission day group. This group was a bit different from the rest. They were less likely to have been admitted from home and more likely to undergo fixation, the percentage of patients with fixation declining as the time to surgery is increasing overall. Now look at the middle panel. It shows an imbalance between timing groups in the strata. But the right panel shows identical strata distribution across timing groups. Here we weighted observation by the inverse probability of their timing of surgery within respective strata. We applied the inverse probabilities to the number of surgeries and to the number of deaths, and it produced the same number of surgeries in timing groups within each stratum. However, the weighted deaths inflated the number of outcomes in the timing groups that were underrepresented in each stratum. Applying the inverse probability weighting created 4 hypothetical populations, all equal in size. And they have the same identical distribution of the stratification variables. But they also have different timing of surgery. We achieve our goal. Each hypothetical population now represents the study population, as if they all had surgery on a particular day. Let's take another look at the effect of smoking on birth weight. This graph shows infant birth weight by mother's age and smoking when pregnant. The green dots are non-smoking mothers and the blue dots are for smokers. You can see age is strongly associated with weight. At the same time, older mothers were also more likely to be smokers. Age confounds the smoking and weight association. How do we block its influence? We condition on it. We compare weight by smoking in strata defined by mother's age, and then we average mean weights for smokers and non-smokers over the age distribution in study population. The following graph shows hollow squares. There are the expected mean potential weights according to age. Blue squares for smokers had they not smoked, and green squares for non-smokers had they smoked. Dashed lines show marginal means for the weight at birth by smoking habit. They are the average of expected means in the population of mothers if they all smoked, and separately in the same population if no one smoked. This graph shows the same data with one twist. The dots are proportional to the inverse probability of age. Notice that the largest blue dots correspond to the youngest smoking mothers in our sample. They will have the most weight when we compute the weighted mean birth weight of babies born to smoking mothers. Similarly, the green dots corresponding to older non-smoking mothers are larger. They represent larger weights. The dashed line shows the marginal contrast between non-smokers and smokers. Here is the stratification formula again. It links the expected weight to both smoking and age. The equivalence between stratification and inverse probability weighting helps to see the role of the exposure probability. Suppose an association between age and smoking exists. Then the marginal mean is expressed through the conditional probability of smoking by age. If there is no association between age and smoking, then conditional probability coincides with the marginal for smoking. So how do we estimate the marginal mean weight? We use the conditional mean given smoking status. Just one more thing, the treatment effect is the difference between marginal means. Well, that's the same as the average difference of conditional means. It's true whether the outcome is continuous or categorical, but when outcome is binary, it's common to measure association by the odds ratio. However, our averaging strata-specific odds ratio will not produce the marginal odds ratio. We say the odds ratio is not collapsible measure. In this case, we can compute the marginal odds ratio directly from marginal probabilities, bold capital 1 and bold capital P naught. In this video, you learned about inverse probability weighting. It's built on a simple but powerful idea. Suppose we know the sampling probability. Then we use the inverse of this probability to modify the proportions of observations in a sample. Let's compare it with stratification. In stratification, we estimate outcome probability by treatment within individual strata. And then we modify the stratum-specific effect by the proportion of the strata in the study population. In the probability weighting, we estimate the joint probability of treatment, outcome, and stratum. We then modify it by the inverse probability of being sampled in a treatment group within each stratum. Here is the main message that I want you to take away from this video: stratification and inverse probability weighting. These two approaches are equivalent. Keep on watching.